Okay. So what does this mean? What does the little ought sign up on top of anything mean? Standard what? Standard state? What's the difference between standard state, okay, pretend that's a state, and STP?
Standard
25 degrees.
One's at 20,
Yeah,
one's at
yeah, that's the
0.
thing. This is really tricky. Standard temperature and pressure. The standard temperature is 0 degrees C and 1 ATM. Standard state is 25 degrees C, 1 ATM, and there's a concentration associated with it, which is 1 molar. Okay, I don't know why they did this, just to mess with you people. But that means at standard state. All right, what happens if you change standard state? I'm happy to tell you that no one is going to change the pressure on you, and no one is going to change the temperature on you. We will, however, mess with the concentration of the reactants and how it affects cell potential. So you could have a standard state cell potential, and it is probably not equal to a cell potential when you change the concentration. Do you get that? Okay, so if you change the concentrations, you probably change the cell potential. Okay, this is really kind of easy. If the concentrations change, this is what you're going to do. Write a balanced equation. Remember, you need to balance for mass as well as charge. And you're going to predict the shift of equilibrium based on the Chatelier's principle. Okay. If a shift to the left occurs, you're going to see that that will reduce potential. And I'll show you here in one second. If you shift to the right, the potential, the E cell, goes up. All right, let's look at this equation right here. Got it? Copper is oxidized. It goes from an oxidation number of 0 to +2. So this is the oxidation. When it's oxidized, what does it do? It's going to lose 2 electrons. 2 electrons go from the anode to the cathode. Okay. Making a flow of electrons. So when this happens in this direction, electrons will move and you will have a positive cell potential. All right. And at standard conditions, the concentration of everything would be 1 molar. All right. Now, let's say that we increase the concentration of Ce4+. If we change the concentration here, what would happen to this equation? Would it be shifted to the left or to the right?
Right.
Mm-hmm. It will be shifted to the right. If it's shifted to the right, you will have more copper becoming more copper ions, and therefore what will happen to the cell potential? It will increase. Okay, happy with that? All right, let's say that you increase the concentration of the Ce+3. Which way will equilibrium shift? To the left. So the cell potential would decrease.
Yeah, was that second? That's just
Oh.
an accident?
Yeah. Didn't even see it. Okay. All right. Now, let's look at this one. For this reaction, we have a cell potential at standard conditions of 48 volts. Predict whether E cell is larger or smaller than the at standard cases. Now, one of the ways of thinking about this is using the term Q. Do you recall Q?
Yeah.
What does Q mean?
It's the K value is not in equilibrium.
It is the concentrations of the reactants or products that may or may not be at equilibrium. It applies here too. So it will tell us that the concentrations may or may not be at standard state. Got it? All right. And to define Q, you put the products raised to their coefficient over the reactants raised to their coefficients. Now, Q did not take into account a couple of things. What? Solids and pure liquids. Solids and pure liquids were omitted from Q, and they are omitted from Q here as well. So we're going to look at this. Our Q general equation for this would be the products, and all that would be the aluminum ion raised to its second power. The solid manganese would not be a player, divided by the manganese ion raised to the third power. These concentrations would determine the value of Q, which would determine whether or not we are at standard conditions. So in our first scenario, the aluminum ion is raised to 2 molar, and the manganese ion stays at 1 molar. Okay, so the aluminum ion is increased. Yeah?
Yeah.
And the manganese ion stays the same. Which way will equilibrium shift?
Left.
To the left. So what can you say about the E cell?
Small.
It would be decreased or smaller than it would be if it were at standard state. Okay. Now,
Right, I thought you said if it was smaller, the potential increases, right? I mean decreases, right? The E side? That potential?
if it shifts, I'm sorry, not equilibrium, if it shifts to the left, which it did, then the potential is decreased, which is what I said.
Yeah.
Okay.
But how come the Q value goes up?
Hang with me for a sec, okay?
Okay.
All right. Now, aluminum is now at 1 and manganese is at 3. This would shift to the right, so the cell would increase. So it would be bigger than the E at standard. Okay, so that would be a nice qualitative way to look at that, but we are all about quantifying things. So we're going to use the Nernst equation. Okay, and the Nernst equation will allow you to figure out exactly what the cell potential is based on the cell potential at standard conditions minus RT. R is the gas law constant that has energy in it, times T, the temperature in Kelvin, divided by the number of moles of electrons times Faraday's constant, times the natural log of Q. Well, that's just going to roll off my tongue. All right.
Do you remember that?
No, I got nothing. All right. We can simplify this a little bit because at room temperature, standard temperature, remember I told you we're not going to mess with the temperature in these problems. The cell potential is equal to the standard cell potential over 0.0592. So we have resolved all of this bit for you. And also gone from the natural log to the log base 10. So it becomes 0.0592 over n. All right, that is much easier to handle. Good?
Yeah.
Maybe. All So here is a sample problem. Determine the standard cell potential and the cell potential based on these concentrations when you're giving the following half reactions. These are both reduction reactions. This is a galvanic cell, so we know that, first of all, we know that one of these has to be oxidation, and we know that the total sum of the cell potentials has to be positive. So what are we going to flip? The zinc. So the zinc is going to go to the ion plus 2 electrons. And now the E will be 0.76 volts. I'm just going to cross that out. All right, so the standard cell potential is 1.76 volts.
What's the V on the 12?
Vanadium. So now I need to do a little balancing.
I've never seen V on the periodic table.
It's always been there, just waiting for you to notice. Patiently waiting. All right, I'm going to multiply this by 2, and that's going to work for me. And so I'm going to, in one go, write my balanced equation. I wish I had a little more room.
So we just, did they automatically do the acid, balanced it for you on the top one? That they used the acid method?
Mm-hmm.
Will we ever have to do both in the same problem?
Oh, maybe.
Because I was asking Oliver and Tara, and they said they had one of these problems on the AP test last year.
Oh, did they?
Yeah, they had a lot of galvanic cell stuff.
They always have electrochemistry on the AP exam. And it's really not given that much time or energy in terms of the curriculum, but they sure like to test on it. And historically, we do really well. Maybe because I loathe it. Okay, so here we go. Now I have the cell at standard conditions. I want to know this. I need to know this, which is?
2.
So I got that part. Now I need to figure out Q. So Q is going to be the products over the reactants. Let's stop and look at I could be very sarcastic and say, do you need to get that?
It's important. It's business call.
It's business. Okay, so we know that this is true, yes? Water will not appear in the Q value, and neither will the zinc solid. So the general formula of Q is, this is just a nightmare. All right. Yes. The zinc ion does, but the zinc solid doesn't.
It's open.
Come on in. We're doing really big math here. There's 2 big. Cute. Love how everyone gets that one in their stomach. Like, oh my God, is it me?
You should just walk up and down the...
I should. And then in the past, I'm not gonna lie, I've done that. All right, so let's get this done. So it's 2, is that right? Now, it is, yes.
No.
Now,
1 times 10 to the negative.
All right, can we skip the math and I'll just tell you that the answer is 4 times 10 to the negative fifth?
Sure.
Okay,
Yeah,
okay. So here we go. E is equal to 1.76 minus 0.0592 over 2 times the log of 4 times 10 to the negative fifth. Do all sorts of math.
Click what?